Okay, so welcome back to our course on the fundamentals of attosecond science and technology, which we bring to you from the Indian Institute of Technology in Madras and at Tirupati. So, we are at an advanced stage in this course, and we further our agenda of measuring the shortest pulses that we have at our disposal, particularly in the optical and infrared domains. So, we will continue with our discussion on this based on the texts which we are closely referencing this discussion to, the book by Roulier, Femtosecond Laser Pulses, Chang's book Fundamentals of Attosecond Optics, and the book of Diels and Rudolph on ultra short laser pulse phenomena. And many thanks to Professor Trebino once again for his inputs and lecture materials. He is also, as I have noted earlier, one of the pioneers in this area of science and technology. So, in the previous two lectures, we stated the problem and the challenge in unambiguous or clear cut terms, where we understood that we have an electric field of a laser pulse, which we write using the intensity I of t and the phase, right, exponent of I of t and phi of t. So, knowing the electric field completely means knowing both I of t and knowing phi of t, but we also realized that the signal measured by a detector essentially is, as far as the durations of these pulses and the optical cycle is concerned, something which is proportional to a quantity like this, right. So, therefore, all time sensitivity is lost. We also therefore realize that if we use the equivalent spectral domain description of the same pulse, which is equivalent and complete in all respects, then we essentially have this sort of a scenario where E tilde of omega is S of omega exponent I phi of omega, right. So, measuring this in either domain makes for a good metrology of a pulse of the type that we have been discussing so far in this course, where we have an electric field, a time, oscillations, a carrier, and so on, right. So, the challenge itself is posed owing to the fact that we do not have a fast enough detectors, okay, and the fact that we do not have even shorter than what we are trying to measure themselves. That is, we are trying to measure the shortest events known or created by man, right. Just a second. So, that is basically the challenge we have here in this entire exercise. Okay. So, essentially this leads us to the fact, as we saw, that we need to exploit self reference techniques to do this in the absence of any cross referencing and standards that are possible. We may sometimes, as we discussed at some point, have some kind of cross reference possible, but not always. The most general scenario, we need to rely on self referencing, which led us to discussing autocorrelation as a possible solution to this problem of interest. We learned that for a more and more increasingly complete description of the pulse, we would need higher and higher orders of autocorrelation, right. So, we have first order, we have second order, we have third order. Up to this, we kind of discussed in some detail what these entail us and so on. But we are going to address in this lecture, we have already done this to some extent in the earlier discussions as to whether autocorrelation is enough. If it is enough, great. If it is not, then what about going forward? Spectral methods, and in particular frequency resolved optical gating and the such, right. So, what is the problem with autocorrelation or incomplete autocorrelation? It is not unique to each pulse. It has artifacts along with the fact that it is incomplete. It has artifacts like it is symmetric about the zero of the delay. This is something we saw earlier. Even if the pulse of interest is not symmetric about its peak or maximum, it is an essentially asymmetric structure in time. It contains no symmetry. Autocorrelation is always symmetric. So, that for example is one of the challenges. Then other aspects such as if I want to do higher order autocorrelation, I need more and more energy in each single pulse, because if the pulses are too weak, we may not get an appreciable nonlinear optical signal, right. Now, autocorrelation is nonetheless a very useful tool because it is quickly done. It is a quick measure to gauge things like, do I have a finite pulse duration or maybe longer, or if I already know something well about these pulses, some pre-knowledge, then I may not need to resort each time to a more complete measurement strategy. Maybe a second order autocorrelation is good enough. So, there is merit to it, but then it does not answer the question in its entirety. That is, it does not tell us, give us a complete, unambiguous, unique measurement of pulses, right. But this is something we might as well demand, both for academic or technical or technological reasons or whatever that may be, but certainly we need to respect the fact that there is such a missing facet in our knowledge about femto, atto, and even longer time scale phenomena. So, just to remind ourselves, the autocorrelation of some very complex pulses, which I would call not so nice pulses at the end of the day. These are not pulses produced by a good laser. If they are produced by a good laser, if I were to get such a spiky pulse as in the third panel to the left, I think there is something seriously wrong with the laser, which hints at maybe a requirement to service it or something like that, right. So, on the other hand, the autocorrelation trace, especially if I go from the bottom, the bottom piece of the the bottommost panel on the right, go upwards, then it could even be misleading in the sense that we would be measuring a strongly peaked feature and the rest is a pedestal, which early on in literature, before better techniques were implemented, were thought to be a truly good measurement, whereas subsequently when better methods were discovered, such as the ones that we are going to discuss in this session, it was realized that this strong peaky spike riding on a smooth background like this is indeed an artifact. It is the coherent artifact. It is merely a representation of the sharpest temporal feature or spike in an otherwise noisy pulse. it's also borne out sort of sequentially over here. Here you again have a nice peaked structure, and of course, what I would ask you to imagine is, imagine that you made a measurement with a finite background. One made a measurement against a finite background where there is noise and everything else. You typically tend to then say, okay, this is a baseline which I do not know what to attribute to, and that the true measure of what I am trying to measure here is in the spike. This is what was actually done earlier, and this I mean in academic pursuit, one tries to push the envelope of science, human knowledge, or what we can do, and producing a shorter feature like this immediately gives you the impression that if you are working to create the next shortest pulse and maybe even get one's name, as I said, in a world world record catalog or book or something like the Guinness Book or something, then this immediately becomes a case, a scenario to make a case that we bested the best efforts, but that need not be true, because this is a reflection of just the coherent artifact. So now, for all these kind of envelopes, right, we now can distinctly say that we have essentially in such noisy pulses a second order autocorrelation of some spiky feature, and the envelope itself is reflected in the pedestal like feature at the bottom. That is the interpretation, right. So, this also points back to a more severe problem, that is, if we get such strongly peaked structures riding on a pedestal, or if we just rely our entire judgment on the fact that we have a strong peak and ignore everything else, the retrieval we may do in inverse Fourier transforming this sort of a structure will not lead us to a correct picture, even if we are willing to admit that we do not need a unique solution. Maybe we can live with a set of retrievals and say, okay, it could be one of these structures, and I do not really bother what the unique answer to this is, right. Even in such a scenario, it is very misleading, because the inversion, the retrieval is very misleading, right. But then understand that when we have things like an unstable train of pulses, we could have maybe, as I said, sources which may not be very well controlled, or we may be building a new laser source, and we may want to avoid scenarios of double pulsing and stuff like that. In all these kind of scenarios, a coherent artifact with just a background, as has been shown here in this bottom right corner, is very representative of what is happening. We have a step like pedestal like feature, and we have a coherent artifact, right. So, these are all some of the challenges in relying only on this information, right. So, interferometric autocorrelation has ambiguities. Okay. Now, we again showed that the interferometric autocorrelation of two different types of pulses, one where the envelope is symmetric and has a sort of gradual rising and a steep falling edge, and this very nicely symmetric pulse, which is in fact even shorter in terms of its measure of full width at half max. So, these two pulses have the same, lead to the same kind of autocorrelation trace. Now, the intensity autocorrelation of a complex pulse, once again, is often dominated by the coherent artifact if the pulse is, especially when a pulse is rather complex like what is shown here in the left panel. Okay, so these are all reasons and the problems which plague autocorrelation as the go to technique. And we saw in the earlier lecture that we want to therefore look at more complete metrology techniques, which would here turn out to be methods that rely on some discovering or determining the spectral aspects of these pulses. And here we, as I said earlier, we go into the acoustic domain and look at the fact that we have these spectrograms which we write on which we write out music, where we have frequency changing as a function of time. That essentially is music, and musical scores live on this time frequency domain, right, in every musical tradition such as the Indian tradition as well, right. So, maybe there is a clue there, okay, yeah, there certainly is, and let us examine that more closely. So, as I said, we can have a distribution that is have such a spectrogram for pulses as well, where on one axis we plot time, which is like a delay time on appropriate time scales where we want to determine the time structure of the pulse itself, and the other on the other axis of frequency, right, the complete frequency at every instant of time, frequency map. So, this now becomes a 2D information regarding the pulse. As I said, this is like a bit like a fingerprint or a retina scan. It is 2-dimensional information, and maybe this will lead us to more unique encoding of pulses as against a 1-dimensional case. Of course, it can also bring with itself its own complexity. So, we rigorously mathematically define the so called spectrogram. So, if E of t is the waveform of interest, then in writing down the spectrogram sigma of omega and tau, where tau is a delay variable and omega is the frequency variable, right. The spectrogram essentially is the mod square of what is the Fourier transform of the product of the field itself, that is E of t, multiplied to an appropriate gating function g of t. So, we have introduced this new entity called the gating function g of t minus tau. Note here that we integrate out t, the time, because the integral from minus to plus infinity over dt and taking the mod square is what finally the detector does. So, this aspect, the mod square and the integral over time are owing to the detector. Any detector that we have at hand can at best do this sort of a thing, right. This is what this is a detector model for the detector or detector model. What we put in is what we can do ourselves. So, we use a gating function and then we Fourier transform this, that builds the spectrogram of these pulses. Therefore, these measurements will depend upon the choice of the gate function too, but understand that E of t itself, this function is to be determined. It is not that we know this. We choose the gate, we measure the spectrogram and we determine E of t the field. So, the left hand side is a signal, on the right hand side there is a gate, these two are in our hands, whereas the signal itself E of t is unknown and is to be determined in this problem. Now, the spectrogram of a waveform, I will call E of t either the field, because it is the electric field of the pulse, or the waveform of the pulse, not just the envelope, right, and we know what we mean by the spectrogram. The process of essentially building the spectrogram or determining the spectrogram is illustrated here, in which case look at the fact that we have a gate function g of t, this is a window function, okay, and this, it is a moving window. The placement of the window about the temporal coordinates of the pulse is determined by tau, which is the temporal variable here, and we can move tau, we can move the gate along, right, forward, backward, and scan the pulse. That is what the integral does. The integral is minus infinity to infinity dt. Therefore, the relative position between t and tau, that is t minus tau, changes, is swept when I integrate from over t to minus t, right. And we do this for every value of tau. So, I can place tau at any intermediate position, and I would actually want to know tau for a substantially large time window while doing this sort of a measurement. So, this helps us build up the spectrogram. The spectrogram, when built up, this is something I know the spectrogram itself, and I have an idea of the gate function. The challenge is going to be to find the gate function itself, which is also something we will have to dwell ourselves upon. We will see what that happens. If we measure the spectrogram and have a good idea of the gate, then we have hope in finding out what E of t is. E of t here is essentially the electric field E of t, and E of t is essentially square root of I of t e to the I phi t. So, I will then determine the envelope and the spectral, the temporal phase, the temporal intensity and temporal phase, or spectral intensity and spectral phase. Here we are actually going to do everything in the spectral domain in reality, and then we will Fourier transform it. Ideally, if I know this and there is a way to retrieve E of t and process the data, I will be able to make this nice electric field map. That is what we are getting at, right. So, the process itself which we have at hand, right, can be imagined to be something like this. So, the gate tau is being moved, okay, from whatever value of tau that I choose. Let me choose a very early value of tau. I am doing all this in a frame of reference which is moving with the group velocity of the pulse. The pulse which is here in the background is what it is. It is travelling at the velocity of light in the given medium. So, stay in the reference frame where the pulse is stationary. That is you are also the measurement. This cartoon is also done in that reference frame. On that reference frame, the gate is being moved, and see how it essentially scans the pulse, right. So, the gate function is doing precisely this, right. So, this is essentially how we scan through an unknown object in various other techniques as well, right. It could be a satellite which is essentially imaging the earth. So, a satellite makes large swaths of, if it has some way of determining this, or a radar for example, is continuously scanning the field of view and making and then processing the signal to present the information that is processed about it, and so that the so called pulse can be discovered. Now, these time frequency maps are a place to go to, because look at the spectrograms for these pulses. If the pulse is linearly chirped, okay, then the spectrogram of a linearly chirped pulse, remember, a spectrogram is a function of omega, which is here on the vertical scale, and delay on the horizontal scale. So, it is a 2D map, right. So, that 2D map for an unchirped pulse is, assume also, a very nicely behaved Gaussian pulse with a nice symmetric Gaussian envelope. If it is unchirped, then the spectrogram is an elliptical figure which is just horizontal in its orientation on the delay frequency map. Whereas, if it is positively chirped, the ellipse is tilted towards upside as delay increases. The major axis of the ellipse has a positive slope. The major axis of the ellipse for a negatively yet linearly chirped pulse has a negative slope. In both cases, this elliptical contour profile is very much present in this case. Okay. Now, what are the properties of these spectrograms and how do I choose the gate function? Now, if I went back to this description of the pulse, I am very tempted to make a proposition here, right. What should be my criteria for picking the gate function? The gate is after all scanning the pulse through like a moving window, right. Now, because we are trying to measure a pulse like this, understand that we are trying to measure also things which have fast oscillations. So, my immediate tendency would be to say, hey, let us get as narrow a gate function as possible, right. Let us get a very narrow gate function. Ideally, mathematically, my best choice for a gate function would be a delta function. Let me scan the delta function in theoretical terms, and in physical terms try and fight for creating a very narrow gate. Now, is that what we actually need, and is that the direction in which we should think about this problem and its solution? Let us see. So, let us idealize the gate to a delta function. What happens when we idealize the gate to a delta function? So, replace the gate g of t minus tau by delta of t minus tau, and then perform this integral. Well, inserting the delta function does at least one good thing, it makes the math very easy, because all this delta function does is tells us that wherever in this integral you find t, replace it with tau, that is the solution of the integral, and retain everything else. So, inside the mod square, as a consequence, we say we will therefore have e of t exponent of I omega tau and mod square. Okay. Now, the complex exponent amounts to nothing. Okay. It is just e of the mod square of, we can take the mod square of this first factor and multiply to the mod square of this factor, we should be doing fine. Mod square of exponent I multiplied by the argument, whatever else in the argument is just 1. Therefore, this is e of tau the whole square, right. So, this, if I have a very short gate function, right, what this tells me is that this is just the intensity of the pulse. I am simply getting the intensity, I have lost out on spectral information. I have lost out entirely on spectral information. That is to say that I cannot measure spectra, I cannot measure fields, I am simply measuring some intensity oscillations. From this, without phase information, we cannot retrieve the pulse. We go back to a scenario like what we had in the case of interferometry. We do not have enough information to retrieve the pulse. Okay. So, therefore, choosing a very short gate function is not a good idea. We want a gate function that is approximately the width of the pulse itself as a consequence. But intuitively speaking, why is this happening, right? Intuitively speaking, why is this sort of a thing happening? That is not hard to see, okay, because of the following reason. Before we do the Fourier transform, look at this quantity, okay, look at this quantity. What does the delta function do? It samples out E of t what does this product do? This essentially, of course, we need to do the integral, but the delta function is extremely sharply peaked at one point, okay, and everywhere else it is 0. So, therefore, this is E of tau multiplied by some very large amplitude for all values of t. Okay, this left hand side quantity is still a function of t. This is now the kernel. So, therefore, I am doing the integral of this guy, this is one constant some kind of a constant value, you can say, exponent of minus I omega t dt. What does this give you? This gives you a broad, almost flat, white spectrum for every value of tau. Okay. So, therefore, information specific to the shape of the electric field and the pulse is lost owing to this very dominant gate function, which is very short. It need not be that this is truly a delta function, right. A delta function can be written as a function, as a limiting case of some other strongly peaked function, right, such as the sinc square function or whatever, right. Aha, there is some other issue. Okay, your screen is back. So, the strongly peaked nature of the gate function is really bad. Okay. So, therefore, a good gate function is about the is similar to the pulse itself. That should actually bring a smile to our faces. A good gate function, okay, is it has a duration similar to the pulse itself. As they say, fortune favors the brave. So, now we braved ourselves into this territory and had some bit of good luck, even if we did not already come into it with great insights. It seems this is a good idea.